Recording going. All right, we're going to dive into Chapter 10, and boy, do I mean dive in. Chapter 3, Lecture 10. It's a huge chapter, not as much coverage as Chapter 1 in its width, but its depth is what really makes the big difference. So here we're going to learn the details of how the magic works on the internet and how we're able to use these inexpensive pipes that no one wants to pay money to upgrade the equipment on and still manage the growth a billionfold of the number of devices that are placed on it. Can you imagine a 9 order of magnitude increase in services from what you'd originally planned? So we'll start with connectionless transport. We'll get pretty quickly to UDP, and then we'll move on to some other things. So UDP is a bare bones protocol. So things can be lost or delivered out of order. It's also connectionless, so there's no handshaking. That makes it faster, and each UDP segment is handled completely independently of the others. So no one even knows what the right order is, let alone that something arrived that way. So every packet has its source and destination IP address and port number. Whereas with a socket, when you're using TCP, you set some of that up and you don't have to repeat it on every single packet. You just pour things into the same socket that's established for the duration of the connection, and it remembers those variables. So you'll use UDP for streaming multimedia apps and DNS and SNMP, but wait, isn't DNS important not to lose? Isn't it important to not get part of a record? Well, there's error checking that keeps that from happening, and just like we talked about before, if you don't get an answer the first time, you're just going to hit return again. There are times when you use TCP. That's when you're updating a database or you have a large block of data that won't fit in a single packet. Then you apply TCP to make sure they show up in order, etc. So if you want reliable transfer over UDP, you're going to have to write it yourself at the application layer. And every app author is going to have to be prepared to do that. So there's a link field in the very simple UDP segment header and a checksum, a source and destination port number. And the goal of the checksum is to kind of detect these errors. And I think we've talked a little bit about the checksum before, but I'm going to just kind of fly through this thing for you guys. You add things up in columns, just normal binary addition. If there's a carry out, you add it back to the beginning. And in this case, there was a 1, and so I'll add that 1 back here and then calculate my new number. Once I have this number established, I flip the bits. I do a checksum of it, and that's the string that I put inside my datagram. That's what I ship across. So if you'll remember, before I transmit something, the checksum's all zeros. I add it all up in 16-bit columns, get a number, send it. Now replace the zeros with this new number, which is the inverse of the sum. So when I get to the other end, what I should have is the sum and the inverse of the sum all buried one way or another in this packet. So when I add the things back up, instead of all zeros, it's got the inverse of the sum. All the rest of the packets represent the sum. So the sum plus the inverse of the sum equals all 1s. And if you look down here, that's exactly what you get if you add it up. So there's a utility on the website to kind of help you play with this a little bit and walk you through it some. What we want to talk about today is deeper into the finite state machine. So we went past this already. I just want to kind of back up and make sure you guys remember sort of where we were. The problem was we have this unreliable channel at the bottom, and we're going to build some things to deal with it. So we talked about the 4 different function calls that we have, and we introduced the concept of the finite state machine, where we have a variety of states with circles, and then you have, and I think this is as far as we got, then you have a series of definitions that cause you to move from one state to another state, not a different state, just another state. So the format for these definitions is an event over an action, an event on top of an action, separated by this horizontal line. So in this case, what I'm basically trying to tell you for this diagram, if I were the author, is I'm in state 1, and if this event happens, I'm going to do the following things, and follow this arrow and end up in state number 2. Now I'm in state number 2. The only things I can do are the things that are defined by these events. So there's an event and an underline and an action, an event, an underline, and an action. So some states might point to themselves. Usually they point to other places, and we'll see combinations of both when we talk about this. So it's simply a map to map out your protocol to make sure you don't have something where you can get stuck, that you've handled all the cases, and it's a lot simpler way before you sit down to write code of sort of explaining what's going on. So RDT 1.0, we're going to take a first pass at a reliable finite state machine, a reliable protocol. We're going to assume, which is a big fat lie, that there are no bit errors and no loss of packets. So the FSM for the sender and the receiver are really simple. I start here. I'm in this state with this circle. I'm waiting for a call from the layer above, from the application layer. And I'm the transport layer. I'm the layer right below. That's the chapter we're on. And then below me, I have network, which is layer 3, data link, and then physical, which is layer 1. Okay, so I'm waiting for a packet from above. That means from the application. When the user up above calls this function, that's an event that I want to pay attention to, then I'm going to do the following. I'm going to pass the data that they gave me to a function called makePacket. And I'm going to store the resulting data structure that comes back at me in this variable. And then I'm going to send that variable over the unreliable data channel. On the receiver, I do the opposite. When the layer below me calls this function and passes me a packet, I will extract from that packet the original data that it contained from the application layer, and then I will deliver it to the application. So I spend my whole life on the sender side spinning in this circle. Every time I get a packet, I go through that event action pair, and then I go right back to the same state and wait again. Okay, so the problem is underlying channels, of course, may flip bits in packets. So how do we recover from errors during conversation? We'll ask for you to repeat it. Excuse me, I'm sorry, could you say that again? What was that? So the question is, how do we recover from errors on the network? We will send acknowledgments back. And what the acknowledgment is going to do is convey to the sender that the receiver acknowledges the successful receipt of the data that they sent. And when we don't get something that the way we expect it, we can send a NAC, a negative acknowledgement, explicitly telling the sender that there was a problem. The packet had errors, it was too long, it was out of order, whatever it might be. So let's develop an RDT 2.0 that includes error detection and this acknowledgement feedback mechanism. So the problem with this is the ACK-NAC, what if that is where the bit error occurs? What if you got the packet fine, you sent an acknowledgement back, and the acknowledgement was corrupted? All the sender knows is he gets a piece of garbage packet. He throws it in the trash. He can't tell what it is. And you can't just retransmit because you might be duplicating the data at the other end. So you must be able to handle duplicates. Well, that's harder because how am I going to tell one packet apart from another? How am I going to know if it's a duplicate or not? Let's add a sequence number to it. So we number these packets. So that sets up the basis for a famous type of protocol that's used to study TCP called stop and wait, whereby we will send one packet and then wait for a response from the receiver. And here's what the FSMs look like. When the application layer up above calls the RDT send function and includes their data as an argument, I'm going to call the function makePacket. I'm going to pass it the data that I was just given. I'm going to give it a place to put a checksum in, and I'm going to then pass that resulting data structure to send packet. It's a variable name, and that's where I'm going to keep a copy of the packet in case I need to send it again. and then I'm going to actually do the sending. I'm going to send it down a layer to the unreliable layer, which is the network layer, and I'm going to insert that. But I still keep this variable. Nothing's happened to this variable. So I'll start my day waiting for a call from above. If this is what happens, I move to this state where I'm waiting for an acknowledgement. And if I get a packet back and it is the acknowledgement, then I'm going to move along and send, oh, sorry, I made a mistake. If I get a packet back and it is a NAC, it's telling me the packet was corrupted, I'm going to resend the packet because this variable still has the same value. I haven't called this function again anywhere, so it's still got the same value. If, on the other hand, I get the packet back and it's correctly received, it's not a NAC, then there's nothing I really need to do. I just transition back to this state. On the receiver side, if I receive something and it's corrupt, I send a NAC. If I receive something and it is not corrupt, then I extract it, deliver it to the application, and send back a thank you note. So we can kind of walk through the way this looks. And so what this animation is going to show you is both sites start in the middle. And let's say somebody calls RDT send, and I'm going to send a packet across. And let's say it's not corrupt. So I end up down here in the bottom part of my receive side on the right-hand side. So I will process this code, and I will send back an acknowledgement. And because I receive an acknowledgement, I match this event action pair, and I will send things back over. Now, what they should have done was colored this in yellow, because as soon as I send a packet, red, I mean, as soon as I send the packet, I'm over on the right side. But you get the idea. And then I'm back in the wait from the call from above again. And let's say this time I send a packet, just as before, but this time it's corrupted. And they got the red circle right this time. Yay! So this time the packet is corrupted. Boo! And so I'm going to send back a NAC. And that's going to match this event action pair. And so I'm going to resend the packet. Let's say this time I'm lucky, it's not corrupt. So I'll run this code to extract it, deliver it, and send back an acknowledgement. Okay, so that's basically the way it works. Now, what happens if the ACKs and the NACKs are garbled? It gets a little more complicated. So this time we're looking at the sender side only. And what we're going to do is double the number of states. Two of them are going to introduce this concept of numbering the packet with zeros, and the other two are going to introduce this concept of numbering the packets with ones. So we're going to alternate, even packet, odd packet, even packet, odd packet. And since I'm only sending one at a time and waiting for the acknowledgement to come back, if I'm sending a 0 and I get an acknowledgement for the 0, it can only be that 0. Because if I had sent a 1 and I was waiting for an acknowledgement for a 1 and I didn't get it, I'm going to stay there until I get it. And the same thing with 0. So these look very much the same. The difference is I'm checking the numbers as I do it. So I'm going to put a 0 in here, and I'm going to stick a 1 in here. And when I get the acknowledgement back, it doesn't explicitly point it out, but you basically are looking for, is this ACK a 0 here, and is this ACK a 1 here? So that's just doubling, but they're mirror images of each other, right? So these things kind of duplicate. On the receiver side, it's two states. You're dealing with 0 and 1 again, but we have a few other things that can go on. So if I get a packet perfectly normal, I send it back, whether I'm in the 0 state or I'm in the 1 state. Either way, so I've got that taken care of, and I've got this one taken care of. If I'm in the 0 state and I sent a packet over, I'm now going to be in this state waiting. So what can happen here? One of two things. I either get the packet back and it's corrupt, in which case I'm just going to send it again, and this is the receiver. I'm going to send them a NAC, send the packet, or I'm going to get it and it's not corrupt, but it has the wrong sequence number in it. And in that case, I'm going to send an acknowledgement back as opposed to a NAC. So there's a difference here. But the acknowledgement I'm going to send back is for packet 0 to let them know I never got the next packet. You sent me another packet. I see that. But the only one I can acknowledge is the last one you sent. So that's a sign for this person that when they are sitting in this state, the sender, if you recall, they get the wrong ACK, you're going to send it again. Same thing over here. If you're in a state where you're expecting to get a 0 and you get a 1, you're going to send them back an ACK for the packet you didn't get. And only if you get the one that you like will you move forward. So it's a little more complicated, but these are, with a bit of practice, elegant. And the one that we're going to build up to in 3.0 is much more realistic for what really goes on in TCP. So we're kind of getting the run at this thing. So what about this 2.1 that we just did? We've added a sequence number. 2 of them will suffice. Why? Because it's evens and odds, right? You've got to check if the received ACK or NACK was corrupted and deal with it. And it doubles the number of states, but you've got to, because you got to remember whether you're in the even state or the odd state. And the same thing on the receiver. You're going to double there as well. But here's the thing. You're still blind with the other side. The sender and the receiver do not know what happened at the other end. All they know are the packets they send and the packets they receive and the action they take based on those things. So here's an explicit example of that the author calls out. The receiver can't possibly know if the last ACK or NACK that it delivered back towards the sender was ever received or not. So what do? Well, they don't worry about it. If their ACK doesn't arrive, the sender will resend it, hopefully. If the ACK arrives and it's the wrong one, the sender will resend it, hopefully. If the ACK arrives and it's the right one, the sender will move on. But in all 3 of those cases, the sender is doing something. They're sending you another packet. Okay, so let's take a look at one more variation of this where we can get rid of the NACK. We're just going to use acknowledgments. We're going to get rid of the negativity on the network. So in this case, the receiver must explicitly include a sequence number of the packet being acknowledged. And I drew that in on the previous diagram, but here we actually make it specific. You're going to acknowledge exactly the packet you want, and you're going to deal with if you get the wrong package. So here's a piece of the sender, and then here's a piece of the receiver. So all we've done is check to see if the numbers completely match up. That's all. So we've kind of talked through that already. Okay, we need more capability. This isn't enough. We need a network protocol that can deal with those things that we've already talked about, but now we want to deal with loss as well. So the new assumption is that packets can be lost, whether they're data packets or acknowledgments. Packets are packets, and any of them can be lost. So we're going to add a checksum. We've done that to figure out corruption. We're good there. We have a sequence number. We've got ACKs. That's great, but it's still not enough. So what we're going to do is wait for a reasonable amount of time for an acknowledgment to come back, and if it doesn't, try again. So we don't assume that the acknowledgments are going to make it back to us, corrupt or not. We can't even assume they're ever going to arrive. So if a packet or ACK is just delayed, and it turns out it's not lost, but we thought it was lost, so we resent the packet or the ACK, that's okay. It'll be duplicated, but the sequence numbers are going to keep us from getting fooled. So the receiver must specify the sequence number of the packet being ACKed, and this is going to require a countdown timer. So what we're going to do when we send something is we're additionally going to start a timer. And if the timer goes off, we're going to resend the packet and restart the timer. Nothing else really in this transition deals with timers. For example, if I receive a packet and it's corrupt and it was an acknowledgement for the wrong one, either one of those cases, I'm just going to do nothing. Why do nothing? Why would I not want to act when I know the packet was either the wrong packet or a corrupted packet? When I was expecting to get an ACK for packet 0. I just sent 0. I'm waiting for an ACK from packet 0. The reason why you do nothing is because the timer is going to rescue you. When the timer goes off in a moment, it will take care of sending things. And it doesn't care why the timer goes off. If you never got a thing, if you got 10 copies of the wrong one, if you got one thing and it was corrupted, if the timer goes off and you haven't received what you expect, as far as acknowledgement, you're going to resend the packet again. Only when you receive the packet, it's not corrupt, and it's the proper acknowledgement, in this case 0, will you stop the timer and transition to this state. The other half is a mirror image of this thing. All right, so what about the performance so far? It's correct, but the performance stinks. So let's say you have a 1 gigabit per second link. That's going to be extraordinarily expensive, especially if it's got 15 milliseconds propagation delay, which is about 1,500 miles. So you're going to be paying, tens of thousands of dollars a month for this circuit. And you have an 8,000-bit packet, so 1,000 bytes that you need to send. So your transmission time on a gigabit per second is 8,000 bits divided by 10 to the 9th bits per second, because that's what a gigabit is. And it's going to take just 8 microseconds to send that packet. And then you're going to start waiting. You're going to wait for the packet to make its way to the other end. And let's assume the site at the other end is sort of instantaneous, if you will. Doesn't need any processing delay or queuing delay, inside the host of any type. And it's going to basically send you an acknowledgement back. So you've got 8 microseconds where you are doing something helpful, and then 30 milliseconds, a lot larger, not just 4.5 times larger, but we're going from micro to milli. And as a result, you're waiting most of your time. Most of the time, this network is sitting around waiting for nature to take its course, for packets to make it. So you can do the math on the time it took me to transmit out of the total time for one cycle, and the total time for one cycle was in sending the packet and then waiting for the acknowledgement to come back. So it's actually 30 milliseconds plus that 0.008 that you took to transmit. So you have a 2.7 thousandths of a percent efficiency. Your boss will be coming to talk to you. So this is basically a very inefficient network, and we're going to look at how to improve it. So let's take a look at how R3.0 does in some other circumstances, like with packet loss. Normally, with no packet loss, you send 0, you ACK it, you send 1, you ACK it, you send 0, you ACK it. Life is good. Things go on. Now let's try dropping a packet. You send 0, you ACK it, you send 1, one's going to get dropped. So there's no acknowledgement for the receiver to send because they've never received another packet. Eventually, however, your timer will go off and you'll resend packet 1 because you expected the ACK by now. And when you resend packet 1, the receiver will acknowledge it, and you're back to where you were before. Things are back to normal again. All right, so far so good. What if it's an acknowledgement that's lost? You send packet 0, you get acknowledgement 0, you send packet 1, the acknowledgement is lost. Well, how does the sender know whether the packet was lost or the acknowledgement was lost, or the packet arrived but was corrupted, or something else? Well, my question back to you would be, who cares? No matter what the error is, you're always going to do the same thing. You're going to retransmit the packet. That's like your answer for everything. So the timer will go off and you will resend packet 1 again. The receiver needs to be able to recognize it as a duplicate, and it does. And it will not send it to the application. It will simply re-acknowledge what it had before. Now, it may have a hint as to what went on or an idea, but it's irrelevant. It'll always do the same thing. When you receive a packet, if it's the one you expect, acknowledge that one. If it's not the one you expected, acknowledge the other one. All right, so what about premature timeout? That's a famous example. So you send packet 0 and acknowledgement 0 arrives. You send packet 1, and for whatever reason, acknowledgement 1 takes a really weird path to get back. And it hasn't arrived by the time your timer goes off. I mean, shoot, the network can just become a little congested. That's all it takes for this to happen. And so your timer goes off, you resend packet 1, but in the meantime, the acknowledgement has arrived. Now, for which packet does the sender believe this is acknowledging? Is it for this one or for this one? Well, it's going to think, because of the state it's in, I guess, it's this one, but they're the same packet. So how can that possibly, make a difference? So we detect the duplicate at the receiver side, and we re-acknowledge it again. This time we receive double ACKs, so the sender needs to be able to ignore that as well. So it's a little more complicated, because when this first ACK is received, you send packet 0, you receive packet 0, you acknowledge packet 0. This thing you've got to ignore. And when packet 0 has arrived, you're back on track again with, with packet 1. Now, what they show is correct, and it's a little more complicated. So let me back up without all the explanations, and let's go through it again and add one more layer of detail. I sent packet 1. I received packet 1. Let's just look at what happens at the sender. I received the wrong acknowledgement. So I will resend. Will I? What's going to happen up here is when I send packet 1 and receive packet 1 acknowledgement, you assume there's an infinite supply of data. So I'm going to send packet 0. And when I sent packet 0, I'm in a state on my finite state machine where I'm waiting to receive packet 0. So I'm going to get an ACK back. It's not corrupt, but it's the wrong number. That's what this one is. So what do you do when you receive an acknowledgement for the wrong number? Extra detail now. You're going to resend the last packet you sent. And so that's what they actually do. And so in this case, it's a duplicate over here. You'll acknowledge it again, and then you'll be back on track. So they can get a little hairy. So here's that stop and wait operation, the diagram that shows you had just this horrible inefficiency. And what we're going to try to do to solve that is to introduce this concept called pipelining, where instead of a stop and wait with one packet, we're actually going to try to do multiple packets at the same time. So we're going to close our eyes and cross our fingers and take a deep breath and send several packets out at once and hope they make it, instead of waiting on one, in the hopes of having more transmissions take place in the time of a round trip. So there's two forms of this type of protocol, and they lead to the second and third examples that we're going to look at that are pretty famous. One's called go back in, and the other one is selective repeat. So if I can send more packets in a window at a time, then from the time I begin waiting for an acknowledgement for the first packet up here, which finished transmitting right here, I'm going to send 2 more packets. So I've tripled my efficiency, but it still is awful. It's 81 thousandths of a percent in utilization. So one of the homework problems you're going to have is how many packets would it take on this network to get an arbitrarily higher utilization? Like what if I had 100 packets being sent at once? What if I had 500 packets being sent at once? What would the utilization look like? So you'll have a question based on that. And then for go back in, you can have up to n unacknowledged packets. And with selective repeat, you can also have up to n unacknowledged packets. But selective repeat's a little more cool because it added a hyphen to the word. I mean, explain to me why. And the difference is with go back in, you only send a cumulative ACK. And with selective repeat, you send an individual ACK for each packet. So if you send only an individual ACK, it brings up a really important restriction, which is you have the ability, if you're going to acknowledge each packet one by one, to send only the missing packet. And if all you have is a cumulative ACK and there's one missing, you can't, and you've received a bunch after, you can't say so, because if you acknowledge any of the ones after, you're implying that you also are acknowledging the one that's missing. So you have to just kind of stay repeating the old ACK, and you don't have the ability to keep packets that arrive out of order. So here's our window that we've talked about before. Here's green packets that I've already sent. Here's a couple of variable numbers in here. I have a window size here as well. These are the ones that I've sent so far. I have room in my window to send a few more here, the ones in blue. So if the application is sending me more data, then presumably this is kind of like a snapshot of what's happening just in any given instant, because if I watch for a second, I'm going to send these packets and they're going to turn yellow as well. As I receive acknowledgments, this is going to slide over to the right. So if I receive an acknowledgment, for example, for this packet and this packet, get this out of here, first few of these, then I'm going to get to redraw my window, because I have a certain size I'm allowed to send, a window size of n, and these are sent. So I'll move my left-hand side here, and I'll move my right-hand side over by 3. The window is still the same size. My send base has moved to here, and my next sequence number hasn't changed until I send more sequence numbers. So that's kind of the way this one's going to work. If I send something, I'm going to move my sequence number over. For the next thing I have, I'm going to make a packet, and I'm going to send it. And if my base is equal to the next sequence number, that means I have a start of a fresh window. So let's say these are green, and I start to send a packet. If I'm here, if this is the next one I'm sending, it matches this case, and I'm going to start a timer for this packet. And then I can send more packets, but none of them are going to match that base condition, and so none of them will have a timer attached. Only one timer at a time, and it's going to be attached to the oldest unacknowledged packet, and that's the bold one here that I showed. Okay, so if I receive data and my next sequence number is outside my base, I don't have room in my window to send this. I've gotten something from the application that I can't send because they told me you can only have whatever it is, 5 packets outstanding, and this would be something that would require 6. So you're going to refuse that data. Okay, that's going to keep you at this state, a waiting state. One other event that could happen is a timer goes off. And when the timer goes off, you're going to go all the way back to your base because the timer is always pointing to the base packet, and you're going to resend them all the way up to the last one that you had sent. So that's brutal. You're going to resend a whole bunch of packets. It's very inefficient, but that's the way go back in works. You're going to go back in packets and resend them. If you receive a packet and it's not corrupted and things look great for you as a sender, then you get to increase your base. This is when you get an acknowledgement back. You're going to increase your base by 1. You're going to slide the window over, and if the base is at the next sequence number, then you can stop the timer. So what that basically means is if the oldest packet you had in here was the only one that had been sent in the window, and you slide this thing over, then there's no more need for a timer. But that's going to be rare. Usually what's going to happen is when you receive an acknowledgement for this packet, you're also waiting on acknowledgments for some others because your window was bigger than 1. So you'll move this over, and what you'll do instead is start a new timer. In fact, I don't need to draw that. You'll move your timer over to this one. You receive an ACK for this one, you start a new timer for this, and so forth. You receive an ACK for this guy, and so on. And then if you receive an ACK and the packet's corrupted, you just don't do anything. The timer is going to go off over here, and it'll take care of that problem. At the receiver, you start off by setting an expected sequence number of 1, and you're going to send an expected sequence number acknowledgement back to these guys eventually, but for now, all you're going to do is make the packet that says, okay, I expect 1. The default thing that happens is you're going to send a packet back. If you get something off of the network and it's not corrupt and it has the right sequence number, then you remember that send packet that you had, you're going to send it. Right? So here's where you're going to do it. The problem is there's no buffering. So let's look at an example of what happens. The dark blue diagram, the dark blue rectangle here is my window. So I have a window size of 4. And I'm going to send, assume I have an infinite supply of data from the application, I'm going to send all 4 packets at once. Packet 0, 1, 2, 3. They all going to go out. Packet 2, the third packet, gets lost. So I receive packet 0, I send an acknowledgement for it. I receive packet 1, I send an acknowledgement for it. Packet 2 never arrives. I receive packet 3, I throw it out, and resend the acknowledgement for packet 1. So what's going to happen is I'm going to receive this first acknowledgement from here. It's going to arrive, and I'm going to go, great. I move my window over 1, and I start a new timer for 1 right here. And now I have space in my window to send a new packet. So I'm going to send packet 4. And my second acknowledgement arrives here. And I'm going to slide my window over again, stop the timer for 1, and start a new timer for packet 2 because it's now my oldest unacknowledged packet, and I have room in my window now that I've slid over to send 5. Life is good. I never get the acknowledgement for packet 2. I set a timer for packet 2. So packet 4 shows up, I throw it out, I send back an acknowledgement for 1. So it's a race as to whether your timer is going to go off or what's going to happen. In this case, I got a duplicate ACK. I'm just going to ignore it. I'm going to let the timer handle everything. And my packet 2 finally times out. And this isn't technically drawn correctly. And here's why. You don't start the timer for packet 2 until it's the oldest unacknowledged packet. So you're actually going to have the timer for 2, but it's going to get started here. And let's say it times out here. We can have it time out at the same place. So what happens when you do that? You go back and you resend 2, 3, 4, and 5 all over again. And you need to, because this guy discarded the other ones anyway. He discarded 3, 4, and 5. So you need to send it on that way. So that's go back in, and I can show you this in action. So let me pull this up here. Here we go. And let's play with it a little bit. So I got to share my screen. Okay, so this is off the spreadsheet. It's called Go Back In. And what I'm going to do is send a packet and speed it up a little bit. And it's going to arrive. The receiver is going to move his window over and mark it. And so when the ACK is received, I move my window over. What if I send 2 packets? And they arrive. My window size at the receiver is tiny. It's 1. You might use this for an embedded device, something really simple. But in the meantime, things are going well. Now you can see a log of what's going on down at the bottom if you want to read in detail as you play with one of these things. So this is great. So what happens if I send 5 packets and on the way there, this one gets lost? What do you think is going to happen? 8 was received. His acknowledgment's on the way back. 9 is what he's expecting, and he's not going to get it. So the question is, what's he going to do with 10, 11, and 12? What Go Back In does is tosses them out. So he tosses the packets out, and he re-acknowledges 8. So we can make an interesting observation here. The network's not dead. The network's actually doing, it's doing okay. I mean, 4 out of 5 packets, in fact, 11 out of 12 packets have made it. So I might not want to be too harsh in assuming that the network has died on me here. There may be a way to improve this protocol a little bit later. So let's let it finish, and we'll see what happens. We don't get an acknowledgement back. You have to be really patient. I don't know why Jim set the timer for this to be so long, but I sped it up. And what's going to happen, the timer is going to go off, and I'm going to resend all 4 of these eventually. Okay, so that's the way Go Back In works. The other protocol is selective repeat. And in this one, we're going to individually acknowledge all correctly received packets, and we're going to buffer them at the receiver as needed in the hopes that the out-of-order packet will arrive. So we're only going to resend packets that need to be resent. So it's going to take more buffer space at the other end. So let's say this is my situation. I've sent all of the things up to here. These have been acknowledged. I'm done with them. Forget about them. These have also been acknowledged, but they're not in the right order. So these 2 packets, I'm still waiting on an acknowledgement, as I am for this one and for this one. All right, so what's going to happen? Down at the receiver side, do I really know what's going on? All I really know is that this packet, this one, and all of these were received. I have no idea what's really going on with the ones that are in yellow. To be specific, I have no idea if this packet was ever received and if the acknowledgement was lost, or if it was received but was corrupted, or if it was never received, or if it was received and the acknowledgement was sent and it arrived but it was corrupted. It doesn't make any difference. I have a timer set for this oldest packet, and what I'm going to eventually have to do is resend it. Now, if we look down at the bottom, it's actually quite interesting. You can tell which of those 4 scenarios I just spit out is actually happened, because the receiver has received all 4 of these packets, and I know this because he's already moved his window over to here. So he obviously received these 2 packets, and he sent acknowledgments back for these 2 packets. So it's the acknowledgments that are at fault. They either were not received or they were corrupted. So he's happy. What's eventually going to happen, though, is the timer is going to go off for these 2, and they're going to get resent, and the receiver is going to ignore them. And he goes, I already have those. Thanks. He'll send the acknowledgments back again, and this guy will be happy. When he gets the acknowledge for the first one, he's going to move the window over 1, like that. But when he gets for the second one, both of these to the left will be green. He'll move it all the way over to here because these were already acknowledged. So he'll get a little jump when that second one arrives. Okay, and with selective repeat data from above, we set sequence numbers, we set a timeout. We are going to move our base over once we get acknowledgments. If the acknowledgments are for outside our range, we ignore them. On the receiver side, you're going to place packet in this array that's got enough room for these receive packets, and you're going to wait. You're going to buffer it and wait for the missing packet to arrive. And when you get it, and when the packets otherwise arrive normally, you're just going to send them on up to the application. Otherwise, if you get a packet that's not in the range at all, like it was an old one or something, just ignore it. So we can take a look at how this works. We go back to our selective repeat, and in this case, my packet 2 was still lost. That hasn't changed. My packet 3 has been delivered. What am I going to do now? Am I going to throw it out? Well, selective repeat says no. Buffer it and send an acknowledgement for packet 3. So on the sender side, I acknowledge 0. I slide the window over, start a timer. I acknowledge, and I have room for another packet. I get my second acknowledgement. I slide my window over. I start a timer for 2, and I have room for and send. In fact, send another packet here. And a little time goes by. I get an acknowledgement back for 3. That happens right here. So I will mark 3 as finished. I still have a timer going for 2. And packet 2 times out. I resend just 2. And then I set a timer for 2 again, only 1 timer. So I'm really, really patient for 4 and 5 to show up because there's not even a timer set for them. I only worry about the oldest one at a time. And in this case, the receipts for packets 4 and 5 did show up. So when packets 4 and 5 show up, I have 2. I had 3, 4, and 5. I'm now ready to finally deliver all these. I have them in order now. And anything else I want to send, it's a cumulative ACK. So I'm going to send back my ACK for 5. Here's the ACK for 4, and 5 arrived. Now, when ACK 2 arrives, what's going to happen? This guy's stuck with his window here. He had set another timer. It hasn't gone off. Let's say this ACK arrives before the timer goes off. He successfully receives it. And now all 4 of these are going to be marked as having been received. What he'll do is slide his window over to 6, 7, 8, etc. Okay? So this is a sliding window protocol. And just remember, you never know what's really going on at the other end. There's a problem with the sliding, with this selective repeat sliding window, though. The problem comes about if you don't pick enough sequence numbers. So here we have a situation where we have 4 different sequence numbers, 0, 1, 2, and 3, and we have a window size of 3. So there's more sequence numbers than there are packets that we can send in a window. That's fine, but let's see how that can get us into trouble. Well, first of all, if we drop a packet, no problem. So I've sent 0, 1, and 2, and I've received 0, 1, and 2 over here. And I sent acknowledgments back for 0 and 1, and that slid my window over, right? When I received 1 acknowledgement, I moved over 1 spot. When I received another acknowledgement, I moved over another spot. And when I moved my window over, I had room to send 3, and then I had room to start over my sequence numbers and send another 0. So 3 shows up, but it gets lost. 0 shows up, it gets sent successfully, but it's a duplicate. Or is it? So we know that it's a different 0. How will the receiver interpret it? Well, the receiver's moved past this one, so he'll correctly assume it's this. Let's look at a worse example. Let's say all 3 packets are sent and all 3 acknowledgments are sent. So my receiver is sitting right here. He thinks he's ready for the first 3, the second 0, and the second 1. But the sender doesn't think any of that. He's never seen any progress at all. So when the timer goes off, he's going to resend the first 0, the first 1, and the first 2. But over here, they're going to be interpreted as out of order, second 0, second 1, and 2 will be ignored. That's a huge issue because I've retransmitted duplicate packets that were interpreted as new packets, and they'll be delivered up to the application just as soon as 3 gets there. So that's corruption, and it breaks the fundamental goal of being reliable. And remember, you have this iron curtain between. You can't see really what's going on. So there's a special relationship between the number of sequence numbers you need to have and the maximum window size you can have. Okay, so let's get into TCP a little bit. And we're doing really well on time. Oh, before we do that, I want to show you the simulator for this one. Like, why is it taking me less time? So let's go back over to our spreadsheet and go to the selective repeat simulator and share my screen again. So same looking kind of window. Send 5 packets. They get there. I have one big window at the receiver side. You see how this one's larger? You see how it's 5 wide now, unlike the other one, which was go back in. Okay, so let's send 5 more. And let's pause and kill one of the packets. Poof, gone. And resume. So I'm sending acknowledgments 6, 5, 7, 8, and 9. Eventually, packet 6's timer will go off. He will resend it. When he does, the acknowledgment will come back. What's going to happen now? I've now acknowledged, when this has arrived, in order from my oldest packet up to 10, the packets that I've received, right? So I will have received all the way up to 6, 7, 8, and 9. I haven't, for whatever reason, I've never sent packet 10. Maybe I was getting ready to do that when all this happened. So what I need to do is slide my window over to the right. And how much are you going to do that? You're going to slide it over enough to acknowledge and push those guys out into the ether. So they're all the way over here. Same thing goes on if I try killing off an acknowledgement to the receiver. It doesn't make any difference. It's just like, you set a timer right now. You set a timer for 11, and you'll just wait. Okay, enough of that. Let's move on to TCP. And what we want with TCP, which has been covered by a whole variety of RFCs, is we want it to handle full duplex data. We'd like a handshake. We don't want to overrun the receiver. We are only going to deal with a sender and a receiver. If we need more combinations, we need more TCP sockets. And we want this to be considered an infinite stream of bytes, a reliable in-order byte stream. We want it to provide the illusion of no message boundaries. And we need it to be pipeline like that United States map we saw a minute ago. So we're going to have to worry about some congestion as well. So here's what the TCP segment looks like. We have room for a source and destination port number. There's a sequence number in here, and we'll talk more about that, but it's basically a serial number that is randomly chosen by each side at the beginning of a connection, and it's used to spot infiltrators. If somebody else is watching what you're doing and they try to step in and fake you out with the packet, it's going to screw up the sequence numbers, and you're going to be able to tell sort of that something's going on. There's an acknowledgement number in here as well. It's also a sequence number, but this is the number of the byte that you're expecting the other side to send. So if I send 1 through 5, the receiver is going to acknowledge that, and he's going to put that acknowledgement in whatever the next packet is that's headed back my way. He's going to throw this in there and put it in. There's some variables that are just 1 bit in length. They're called flags, and these are really critical to setting up and tearing down connections, and then this one tells you whether you should pay any attention to the acknowledgement number. The number of bytes that the receiver is willing to accept so that we don't overrun them is stored here. You can have options, and then the data that you've been built to carry that your application gave you, finally, that goes down here at the bottom. So here's my window size again. I still have a window size of n. I have some things that have been sent and acknowledged, things that have been sent but they're not yet acknowledged. We call these in-flight packets. Things that haven't been sent but I can at any moment as soon as I'm given them because they're within my window. And then these are unusable. Most often what happens is this is pretty much full all the time, and you have packets that are waiting. How are you going to handle segments that arrive out of order? You get to pick that on your own. The protocol doesn't specify that. So this is a sequence number. It's the next byte I'm going to send. It goes right here. If I'm trying to acknowledge something that I've received, that acknowledgement number goes in this field, right here. And I'll set the flag here because that's what the protocol says to do. Okay, so let's look at an example. I have these sequence numbers, and for whatever reason, these sequence numbers don't start at 1 or 0. Well, I told you that we pick random numbers, right? So in this very first packet that A is going to be sending to B today, he's telling the receiver, I'm going to send you a packet. The first byte number is going to be byte number 42. That's what I'm going to call it, 42. So here it comes. And in this case, this packet happens to be weird because it only has 1 byte of payload. Is there really an application where you only send 1 byte of payload? Yes, Telnet. Telnet only sends 1 byte at a time. And I know this isn't the first thing that's gone on around here on this network because the host A is also acknowledging having received some bytes from host B, and he is telling host B, I am ready for you to send me next packet 79. And then he, of course, includes the data. It's acknowledged. You told him, I'm ready for you to give me 79, and here is 79. So he sends that back to her, and he successfully receives this 1 byte. That's byte number 42, and so the receiver will tell the sender, send me byte number 43. And so she does. She sends him byte 43 next. And assuming byte 79 was successfully received from the host A will acknowledge that by saying, I'm ready for you to send me byte number 80, for example. Okay, something weird going on here that I need to point out before we wrap things up. And that is that you always, in reality with TCP, you always acknowledge the next byte, the one after the one you received, the one you are expecting to receive next. Why? Because the math is really easy. So let's take, for example, I start at byte number 90 and I send 10 bytes. What's the last byte number? Aha! It's not 100. It's 99. Don't believe me? 90, 91, 92, 93, 94, 95, 96, 97, 98, 99. That's 10 bytes. But we always think that 90 plus 10 is 100. Well, it is in our numbering scheme, but when we're sending packets, we count the first one. So to make this easy, I will just do the normal addition because that's what the CPU is going to do as well. And I'll add 90 to 10 and I'll acknowledge 100. So the way to think about it is you're always acknowledging the next packet you expect to receive. One other thing that's important here to kind of visualize, the application is sending you this infinite stream of data that comes down this very long garden hose and it's just pouring out the bottom. You have cups that are a certain size. And you can fill these cups up only with a certain amount of water, and the size of the cup is going to be defined by a variable in a minute. But you fill this up with as much water as you can, and then you have permission, you have room on the truck, you put it on the truck, and you send it towards the destination. That's a window's worth of water that you're sending, but it's a continuous stream. And so the size of the cup and how many cups at a time you can do is completely arbitrary to the application and invisible to the application. There's at no time you ever tell the application, look, here's how big my cup is. Do you mind just giving me this many bytes at a time, this many bits at a time? So what you're going to do is number these bits by 8 at a time as byte numbers perpetually. You're going to number them in this scheme byte at a time. So this cup might start with byte number 600 and contain 42. The next one may start at 642 and contain 18. It doesn't make any difference to the application. So just remember, it's a continuous stream. What we need to do now is to figure out what we're going to have happen with the timer. So we know from our diagrams that it takes a certain amount of time for something to arrive at one end and for a response to reach us at the other. And we've been calling this round trip time, right? So RTT. So we want to set our timers so that we resend packets. But if we're not careful, we'll set them too short and we'll retransmit unnecessarily because we're just too impatient. So think about that when you're just hitting the return key on your browser over and over. Or we could make them too long and we're waiting needlessly for a packet that's never going to arrive. Think about that while you're hitting the return key. So, you may be right on this one. So too short or too long, kind of an issue. So we want to actually calculate round trip time. And the way we're going to do that is by taking sample measurements. We'll measure some samples. Every packet that goes and comes back, that's not a duplicate. We're going to measure the amount of time it took. And we're going to average that in to our running average of sample RTT. And the formula is basically weighted towards what the average is now. It's, in fact, if you let alpha be an 8th, then 7/8 of your new estimated value are going to come from the current one. But 1/8 of it, you're going to allow it to be varied by this. So if the new sample, the one that you just got for the packet that just got acknowledged, has a really big round trip delay, then it's going to nudge this number up a little bit, and you're going to end up with another one. So it has a smoothing effect, as you can see. So this is the real round trip time, and the pink line is the smoothed average. We actually need to do a little bit more than that because we found in practice that we needed a little safety margin, and so we're going to take 4 times the standard deviation or the deviation of this, and this formula basically shows you that. There's a simulator that actually covers this, and let me share and I'll show you. I haven't played with it for a couple of days, so I hope I can find it quickly here. Let's see here. Oh, down here. ACK numbers. Yeah, so there's an ACK number simulator as well. That's kind of cool. But here's the one for round trip and RTT. So every time you pull it up, you're going to get a different set of values, and they're basically going to ask you to calculate the variables that I just showed you. So you're going to have a homework problem like that. So you can practice here, and you can always show the solution by just clicking on this at the bottom. Okay, and I just picked a random one to give you guys. All right, let me think if there's anything else I need to share with you guys before we finish. I think that's as far as I want to go for this hour. And I recorded the next hour. In fact, I recorded it 4 times. I didn't record all of it 4 times. I finally convinced myself that it was an impossible task because these 2 lectures are together. They both deal with the same chapter and the same single lecture, and there was no way for me to predict exactly where I was going to wrap up today. So I guessed wrong, and the second hour actually starts about 15 slides or 10 slides back. So I'm going to re-record it right now and continue on, but of course I'll do that by myself and throw it up there as a recording for you guys, and Hassan's going to take over now. It's a good time to ask for some hints and help on the homework. I'm sorry I haven't been able to answer all the messages I've gotten in the last few hours because I've been working and I've been unable to sort of break away from that. And I think some of those questions are very suitable for Hassam anyway, particularly since it's really up to him on things like, extensions. I'm not going to grant a whole class extension. I can't do it. The class moves too fast. Homeworks on the weekends, like I told you guys, are the hard ones. You got to set aside more time for those things. So if you fell behind, maybe Hassam's got a hint for you or something, but you're just going to get buried if you start dragging it out. You got to find a way to kind of get back on top of it. That's what happens with a 1 month class. On the other side, you're going to master this a lot better than you would taking it during a semester.